Ah, yes. AI. Hmm. How I wish I could actually apply this to something. Perhaps something like metabolites. Hmm. That might actually be a good idea. Metabolites. A very typical thought of someone of my caliber.
So before we get into my project, what exactly are metabolites? Basically, they're these molecules that are analyzed, documented, and researched as part of a field of research called omics, specifically metabolomics. Now let me explain in smooth brain terms. Let's imagine we have a banana. Okay, banana. Essentially, when you eat bananas, bananas go bananas inside your stomach. Your stomach is all like, yeah, bananas, and you're like, yeah, bananas, and it all gets mixed up down there. The banana molecules go do banana things inside the body, and the body works with the banana molecules to continue to essentially keep you alive. This banana molecule is called a metabolite, and in this case, it could be something like fructose. Fructose travels through a long and complex network of metabolic pathways. These metabolic pathways are a huge part of what keeps our bodies functioning and makes sure everything that goes in our body or is already in our body goes to where it's supposed to go. In the end, the fundamental thing to understand about metabolites is that they're the intermediate or end product of metabolism. So now we have a basic understanding of how metabolites metabolize. So let's get into my project. Yeah, so I kind of forgot to talk about the most important thing in this video, other than the project itself, which is essentially. So let's speedrun this real quick, shall we? So in essence, I use the mass spec database, a database formed by a set of 16 research groups that contains the data on electrospray, ionization, metabolic compounds, synthetic drugs, and many other random things I can't pronounce. There. Now let's move on to my project. Okay, so before I go through what exactly this program does, I'll provide a brief outline of the function of this program. This program, when given a set of unlabeled data, is meant to be able to accurately match the unknown labels to a set of known labels. Essentially, what this means is that it's supposed to be able to train using training data to be able to assign labels, in this case, molecular compound formulas, to a set of testing data. So here we actually start with some basic imports. So we of course have number processing imports like NumPy, Pandas, Seaborn, TensorFlow, Matplotlib, and MySQL connector for connecting to our SQL database. TensorFlow is just for cloud computing. And we have some model specific imports, which are just imports that are specifically focused on optimizing the model. From there, we move on to connecting to the database. I don't have my um, credentials plugged in here for the sake of security. Um, but anyway, when you're using the program, you are able to plug in your own credentials for your MySQL database that you may have set up, and you can use that to connect and use the data from there. So the first thing we actually perform here is an SQL query, which is meant to select relevant columns from the compound table. And essentially what this does is that we have a sort of SQL command wrapped inside a Python string, and we use the pandas library to read the SQL within the Python string and put it into a usable form. So from there, we just do a little bit of initial pre-processing, which is just to remove the empty rows. This removes the sort of confusion that might be associated with the model trying to learn from the lack of or null data, essentially. And from there, we actually create an array. Um, X is an array that's supposed to store values from uh, the CH exact mass column and CH exact mass significant, which are two columns that have to do with that are found inside the mass bank database. The second thing is the target variable. So the target variable y, which is predicted using values from columns that are found in the X array, is the CH formula column. So this is specifically the value that we'll be predicting. We'll be predicting exactly what chemical compound we're dealing with according to the exact mass and exact mass significant. Now, here's just some initial verification. It's just to make sure that there isn't any misalignment within the shapes. And from there, we just display the different data sets. This isn't necessary either. So from there, we actually divide the data into training and testing data sets. So this is really important for the model to be able to assess itself as well as use this data for training. So it's kind of making sure that you can achieve both with a single set of data. So from there, we just apply, we use the NumPy library to be able to distinguish some unique labels from Y training and Y testing to make sure that we're dealing with the same amount of labels. And this ensures that we don't have any mismatching between the shapes of each of these variables. So this makes it easier for them to be compared, and this makes it so that computations aren't dealing with different levels of dimensions of data. So from there, we take away any of the unseen labels, and we use actually what's called a mask to achieve this. So here we find the indices of rows that contain previously unseen labels in both training and test sets. And from there, we actually filter the data using the masks. So essentially what the mask is it's just a binary set of matrices, or a matrix of binary values, true and false, things like that, that we can use to sort of assess whether a value is whether we have the correct values in the correct space, whether we're dealing with the right sort of labels, those sort of things. Just another component of pre-processing. And after that, we have pre-processing for the filtered data. This essentially just makes a scalar object that we use to sort of essentially squish all the data into a format where it can be easily compared and computated so that the computer doesn't have any problem using that to learn and assess itself. And from there, we create a label encoder that's just supposed to put the labels in a form where the computer can actually use it, the AI agent can use it, and from there it's just some more components to label encoding. And here we actually define the model architecture. So this neural network is actually made of 3 layers. So I'll just provide a brief explanation of neural networks. It's essentially just a network of individual neurons that form layers. Each neuron essentially represents a number and performs a specific computation on a vector of inputs, and uses those values to form a prediction on the value of these things called weights. These weights can be understood as a sort of gradient shaded value that represents a sort of shaded region within the layer. So essentially, if we had a diagram, it would just be a set of inputs and a set of outputs and a bunch of layers that essentially, as you pass the input data through each of the layers, the predictions get better and better over time. So after that, we compile the model. We create a model object here, and we use the compile method to optimize it first of all, so that we have a defined learning rate here. If the learning rate is too high, it will cause the model to overfit, which is essentially when it becomes too good at the practice test. And from there, we have the loss function we define here, which is just categorical cross entropy. I chose this one because we're dealing with multi-class data, not binary class data. So that means that we have more than 2 possible classes that the data can be sorted into. And from there, we actually have the metrics that we use to define success for the model, which is essentially just accuracy. High accuracy equals model is doing good. So from there, we actually define early stopping criteria. And the early stopping criteria just makes sure that we can keep watch of the value loss and make sure that if the value loss is actually going on a downward trend or isn't improving for over a course of 10 iterations, then the model will actually just stop training because it isn't effective. From there, we train the model, and we define a few properties, and we pass in a few attributes. One important thing to note is the number of epochs, which is essentially the number of iterations. And another thing to note is the batch size, which is how many sort of data points that we can fit into each iteration. So from there, we convert the encoded labels to one hot encoding. This is just some more pre-processing. Well, not pre-processing. This is just putting it back into a form where we can close the database. And from there, we make predictions on the test set. This is where the actual sort of AI component of making sure that the model actually can get stuff done comes in, and we use that prediction output to form an analysis on how good the model actually did. And this is reflected here, where we calculate the test loss and the test accuracy using the evaluate method, where we take the scaled and encoded values for x and y, and we plug it into the model, and we use it as input to make sure that we have a low loss and high accuracy, and we're able to use this information to assess whether the model did good or not. And from there, we generate a quick classification report. This might not actually be necessary, but it's nice to have on hand because it gives sort of an overview of the different components where maybe the model could have improved on. And from there, we just close the connection to the database. So that's a basic overview of how the program works. There's like an in-depth explanation of the code inside the article I wrote, and of course there's GitHub. There's a GitHub repository for this program. You can access the code there as well and take a look for yourself. Maybe correct a few things I could have done better. So yeah.